EEE145, Chapter 6, Protection Fundamentals 1. So let's go ahead and go over some introductions and definitions. So as you recall, the main goal of the power protection scheme is to mitigate damage, right? We don't want equipment to break. We don't want to spend money to replace it, right? So mitigate damage to the grid by disconnecting the affected area. So whatever the problematic area is, basically where the fault is, you want to just disconnect it from the rest of the system, right? That way the system can keep running, it's stable. We disconnect the faulty system so that the public safety is better, and we could go and repair it, right? Because at the end of the day, we won't bring it back into service. So relays themselves make the decision to do what type of function? Well, I like to call it the brains of the operations. They're the decision-making process. They're the decision makers. So we make the decision to trip the circuit breaker. Remember, we only want to trip the circuit breaker when there's a fault. We do not want to trip it under normal loading conditions, right? Otherwise, we're cutting customers off. So this decision making has to be very complex sometimes. It has to be very accurate, and you have to make sure you have to account for all possible situations. So it's kind of like honestly, it's kind of like computer coding, right? Except you're not allowed to, you're pretty much not allowed to make mistakes. So you just got to be very careful about it. So characteristics we want to look for when we're deciding what type of relay or protection technique we want to use. Well, remember, some of the things are speed. We talked about the longer the fault is on the system, the more damage we're going to do. So the faster we act means equals less damage, or even no damage if we act fast enough. Another big factor we have to do is coordination. All right, we're not just going to have a single relay for the whole power system. We're going to have many relays working together. So we're going to overlap some functions. We're going to build backup systems, redundant systems. So we're going to have many relays working together as a team, right? So we need to designing relays to act as a group to minimize damage. Now, there's three major types of protective relays we use. We use what we call a distance relay. We can use a differential relay. Or we can use something called an overcurrent relay. Now, we're going to talk about all three of these. This week, we're going to talk about our overcurrent relay. Next week, we're going to talk about distance and differential. Okay. Overcurrent relay is probably the most common one you're going to see in a power system. So I think it's worth taking a whole week just to fully understand, or at least get the basics down of how overcurrent relays work. So overcurrent protection relay types, right? Now, first thing is, what is the most basic check we can look at the system to see, is it healthy, right? What's the just real quick glance? Well, remember, damage is done by heat, which is done by current, right? Too much current equals too much heat for too long. So the most obvious solution is just to watch the current level, right? So as long as we're constantly checking the current level, the current gets too high, we know we're in danger territory and we need to do something else, okay? And that's why it's called overcurrent. It checks for current that's over a threshold, and then something, it will trip or act on that threshold. And we program that. Now, remember the ANSI number charts? They're there for a reason. Overcurrent has its own special group. So a 50 relay, if you look at ANSI chart, it's called an instantaneous overcurrent relay. Okay, instantaneous means now. So if you just look at the wording, the relay, when it sees an overcurrent right now, it will trip. Okay. A 51 relay, on the other hand, is called an inverse time overcurrent. So here you could think of, well, it's going to check overcurrent. It's going to probably have a timer, and this timer is going to be the inverse of current. So when you think of inverse, it means opposite correlation. So most likely a very large current will have a very short timer, and then a very small amount of current will have a very long timer, right? So it's not proportional, it's opposite or inversely proportional. So we just call it inverse time overcurrent relay. And these two are so common in the power system, and they overlap so many times that most manufacturers build a kind of combination relay. So we call it a combination or combo relay. I guess the technical, let's not use shortcuts. Combination relay, okay? Of both an instantaneous and inverse time over current relay. Okay, so it's basically dual function. Because as you'll see this week is most likely where you have a 51 relay, you also have a 50 element with it, and they kind of work in tandem together. Okay. So the big thing is you have 50 and 51 for overcurrent protection. Now, next question would be, where do we see these in the power system? Typically, overcurrent relays we're going to see in distribution, on feeder protections. We'll say even transformers have them, right? All the way down to industrial level where you have motors, right? You'll have overcurrent all over the place in any industrial settings, okay? So distribution industrial is very common. On any transformer, you'll typically have some level of overcurrent relay as well. They're good, cheap backups. And then generation as well, okay? So on the very small devices or like feeders or small or low power feeders, buses, and like even lighting, you'll have very simple overcurrent protection. Even your house has overcurrent protection. It's your breaker box, right? At the higher, more expensive items like transformers generations, we're going to have other protected devices like differential protection, but it's always good to have a backup plan, right? We always want a plan B, so overcurrent protection can be a backup to a more sophisticated protection scheme in a transformer and generation setup. Okay. Now, question is, where do we tend not to see overcurrent protection, right? It's mainly in transmission. We used to have it a lot, but we kind of shied away from it because the relay is too basic, right? Meaning there's not that much functionality past just looking at current, right? And on transmission systems, it's very complex because the mesh system with bidirectional energy flow. So a simple overcurrent relay it's very, very hard to properly coordinate with other transmission lines, right? A lot of blackouts in the history of power systems have happened because overcurrent protection of transmission lines, you can't coordinate them correctly, and it inadvertently does more damage than good. So we pretty much said as an industry whole is, let's not use overcurrent protection of transmission lines. Let's use something more sophisticated called distance protection. So yeah, you won't see overcurrent on transmission systems. Now remember, for the ANSI charts, there's different, not only is it 50-51, but there's also letters attached to it, so you could kind of get an idea what location this overcurrent really is. So for N, this would be a neutral, instantaneous 50. So instantaneous overcurrent. Oops. Overcurrent relay. Okay. And then a 50M would be a motor instantaneous. Instantaneous. Oops. Yes. Overcurrent. Okay. And then 51G will be a inverse. Oh, sorry. We should write what G stands for now first. It's typically ground for overcurrent. Some people might say G stands for generator. It does on other relays, but typically 51G, 95%, 99% of the time, you're talking about a ground relay. Okay. So ground and 51 is inverse time over current. Okay. A 51T is a transformer. Inverse time over current. And then we talked about before, 50-51 is just kind of we call it, it's a combination relay. I call it a combo relay. I'll put combo in quotes because that's not like the actual technical term. Not everybody's familiar with that. Okay. So instantaneous, neutral, motor, ground, transformer, combo. Yep. So, and there's many more. These tend to be the more popular ones you'll see depending on what line of work you're going to do. Okay. Now, we talked about overcurrent. What do they look like out in the field? That's always a big question when you go out at a substation or motor control center, right? Mechanical relays are most likely going to be black with silver everywhere because that's the metal. And if you ever look closely, there's going to be springs, discs, and screws and nuts and bolts because these are mechanical devices. They run off mechanical principles. A newer digital relay uses a microprocessor. So some people call it digital. You also might hear microprocessor based relay, right? Obviously, you can see here, this is more of a kind of LCD screen with some some buttons and some LEDs to light up. So it's a more modernized digital computer-based version of the relay. They're both overcurrent relays, and they try their hardest for the digital relay to supersede and copy the mechanical properties so that you could directly replace them. Okay, so look at this here. This is your panel. So you got one panel here, one panel here. So different panels. And you can see this middle panel right here. This is a combination of your digital and mechanical relays. Okay, you can see blue is your digital relays. There's a couple black ones left, those are mechanical relays, and all the other panels are all mechanical relays. Okay, so anytime you go to a substation, it'll be pretty obvious which ones are more digital, which ones are all mechanical ones. Okay. Now let's start talking about how does the mechanical overcurrent relay operate. Now we always talk about explaining mechanical relays because they were the first, and the entire power industry's protection schemes are based on these mechanical relays because they're already there. It's so imprinted in our industry that microprocessor relays literally mimic the exact or try to mimic the exact properties of mechanical relays. Okay. So anytime you have a mechanical relay with these discs and springs and whatnot, there's the digital relay equivalent, which just mimics the old mechanical one. Okay, so let's go ahead and try to figure out how this mechanical computer or analog computer work. So first thing is in any relay, remember relays, we draw in a circle, okay? And we have some type of wire coming in from the CT. Okay, where does this come in? Well, this is the current coming in. This is your input. So wire goes in, wire goes out. Okay, so this is your input from your CT. Now, where does the secondary current flow into mechanical relay? Well, it flows right here. We call this into the pickup coil. Okay. So everything in yellow, this is we call the pickup coil because it picks up the current. And then current will now flow through these windings, which will create an electromagnetic field, right? So the electromagnetic field is where's the electromagnetic field being produced? In the pickup coil, through the poles, and the poles are the big solid pieces of metal. As you can see, the piece of metal is cut in the middle, and the disc that slides into it. So the pickup coil produces a magnetic field, and it goes through the poles and disc. Okay, so you can almost imagine the magnetic field just kind of doing this. Okay, going through. So that's the first input side. Is all you gotta know is current goes in, creates a magnetic field that goes through the disc. Now, next question is what happens when an electromagnetic field travels through that disc, right? Well, through electromagnetic properties, the disc will actually start spinning. Okay, so if we put a lot of current in, it's going to create a stronger electromagnetic field. Okay? So a stronger that's a magnetic field will turn the disc. Okay. So basically, you will physically see this disc start spinning. And while this disc spins, you have this moving contact right here. You guys can see that. Okay, this moving contact here is all fixed to this rod. Okay, so this is all one moving part. They move together. The disc spins, that moves as well. Okay, they're all glued together. So as the disc spins, the quote moving contact also spins, right? And this moving contact will spin towards the fixed contact. Get some more room. Okay. So you can see in green, this is kind of path that it'll take. It'll swing over from kind of this way and all the way down like this. Eventually, the moving contact and the fixed contacts will touch each other, and then a circuit is completed, right? And so maybe we'll probably even write that. So this moving contact will spin toward the fixed contact, and then when both contacts touch, we trip the circuit breaker. Okay. So basically, there's some property as current flows in, this starts spinning, and the contacts eventually touch each other, and that's your trip circuit. and then everything just circuit breaker starts going and we disconnect the circuit. Okay. Now, question is all right, so now I know current flows into the relay at a certain point in time, the disk will start spinning and it'll trip the circuit breaker. All right. Now, the big question is how can I control how much current will cause the disk to spin and how fast would the disk spin? Because the faster or slower the disk spins, the more time we're giving to the more time delay we're putting into our decision-making process. Okay. So sometimes you'll hear people say, how do you increase the sensitivity of the overcurrent relay? So what does increase in sensitivity means? Basically, less current is needed to make the disk spin. Right? Oh, sorry. Oops. Disk with a K. Okay. So it's mechanically, we've chose a specific type of metal and wires and core that there's a minimum amount of current needed to make the disk spin, right? And we can program that minimum amount of current mechanically, okay? How can we adjust the relay to react to different current levels? Well, we can change the taps. Change the taps. And what are the taps? These things right here. This thing, these 5 dots right here, these are positions called taps. And we could change the wire to different points or different of these windings. And then what it'll do, it'll change our N ratio here. Okay, so changing the taps can alter the strength of the magnetic field. Okay. Now think about on the side, I'll say taps are kind of like turns ratios. Okay. So if you, depending which tap you choose, you could literally alter the turns ratio of the transformer, making the magnetic field. Okay. So if you put a tap all the way to the bottom, you're going to put a lot of turns here. So you're going to change the magnetic field versus putting the wire at the very top tap here. You're going to alter your N ratio. You're going to change the magnetic field strength. And thus you could change the amount of current it takes to make the disc spin. So we could go from tap 4, 5, 6, 7, 8, 9, 10. And that will be a certain amount of current level needed to make the disc spin. And that's how we can program the relay, by mechanically changing the turns on the transformer, maybe the spring rate in the disc, this type of stuff, okay? So the general thing I want you to get out of this is in mechanical relay, current comes in, creates a magnetic field, make this disc spin, and the spinning of the disc, eventually contacts will hit, and then you'll trip the circuit breaker, okay? That's the big picture of mechanical relays. And like I said, mechanically, that's how it operates. And then we could talk about microprocessor relays. They just use literally hard programming, but they mimic the exact function of the disk. So there's a lot of mathematical models to, like, literally physics mathematical level models to mimic the speed of that disk and the magnetic field, okay? So in the end of the day, just remember a microprocessor relay has the same tap settings and same time down, all those mechanical relay aspects is pre-programmed and mathematically modeled in a microprocessor relay. Okay, so we talked about taps. That's obviously a big part of the mechanical relay. Now, I'll say old school mechanical relays are called taps, but in a microprocessor relays, they swap over called pickup. So if you ever hear pickup and tap settings, it's pretty much the same thing. Okay, pickup and tap are equivalent. Okay, I say tap a lot, so I might inadvertently say tap when I mean pick up, and so you could just swap them back and forth. Okay. Now, first thing we need to ask ourselves when we have the mechanical relay and we're trying to choose what current level would it take to operate the relay, well, we need to know our bounds. What's good and what's bad, and where does a relay, we kind of put that in the middle somewhere. Okay. The first decision we need to make is how much current is considered bad for your system. Well, there are a couple of things we need to know. We need to know the minimum fault level, fault current. Okay. So when we do our system study, what's the lowest amount of current we will see that's considered a fault on our system? So we need to make sure the relay can pick that minimum level fault current. The other part we need is a maximum fault current. Okay, this is literally a worst case scenario. So we got to make sure our relay can act fast enough to get rid of the fault during a maximum fault event. So this is to make sure that the relay will act fast enough. And then minimum fault current is there to make sure the relay will still see this, right? Because a minimum fault current means the current level is not that high. So if I choose the wrong tap setting on my mechanical relay, I might actually have the tap setting too high, and the minimum fault current will just go through the relay and the relay won't even move. The disk won't even move. It'll just sit there and think everything's okay, and then you're going to burn the system down. Okay, so that's why you need to know that minimum level, right? Versus, and then the maximum one is we want to make sure the tap is low enough to where when the maximum does happen, we trip almost immediately and not wait like a whole 2 seconds or something crazy like that, because then the whole system is going to go down. Okay, so there's a lot of kind of wiggle room of where the correct tap setting is, and I'll tell you this, most likely at least half of all protective mishaps and disasters has happened is because people don't put these tap settings correct. Okay. So here's a golden rule of thumb that everybody should know. Okay. Remember, we talked about 3 stages. You got your minimum fault current. We need to make sure we must trip at the minimum threshold. So we need to make sure our relay pickup, our tap setting is below this. Okay. But we don't want to make it too low that we trip under loading conditions. Right. So what happens if you're just sitting here, your AC is running, everything's running in your house, you're not causing a fault. But if I set my relay too sensitive, it might see that your house is a fault because you have too much low current, and then we'll kick you offline, which is terrible because now we're dropping customers for no reason. So we need to make sure at the maximum load, we no trip. Okay. So there's kind of a middle ground here. Okay. So make sure we're above maximum load, but below this minimum fault current. And this middle ground is where the relay pickup should be set at. Okay. The general rule of thumb, as you can see, this is your ideal set point. Okay. It should be 150% of full load amps. Okay. You might see it's called FLA, full load amps. So whatever we do our load system study, you've done that in 141, EEE 141, figure out your maximum current in this area, your tap or pickup setting should be 150% of that full load amps. And we want to do that because we want to give ourselves a 50% buffer room in case something bad, you have some transient or some anomaly happens. Okay. And then of course, you need to make sure that this is 50% of your minimum fault current. So you remember you see it's 2x more. So this should also be, tap setting should be 50% of the minimum fault. Okay. So that's going to be that middle ground we're talking about, where whatever the minimum fault is, your pickup setting wants to be half of that. Whatever our load current is, we need to be 150% of that, right? So 50% more. And hopefully in your system, that range is pretty wide, so you have a little bit of wiggle room. right? And unfortunately, some protection engineers, you get to the point to where that window is so small, they don't really have a choice. And that's where the real hard decision making for protection engineers come in. Okay. So just the big one to remember, to be honest, is really this one. Okay. That's the big one. Okay. More likely, the minimum fault current at your level is going to be much higher than the full load amps. That won't be an issue, but it's definitely one to check. Okay. So just burn that 150% full load amps into your brain. That's what we're going to use all the time and probably for the rest of your career as a power engineer. Now, we talked about full load amps, FLA. Well, I need to know how to even calculate full load amps, where to find, right? If I don't know about full load amps, I can't even do any of my settings yet. How do we calculate low current for new relay? There's two methods, right? Here, if this is a feeder and your relay is your protecting feeder, so this is called feeder protection, you need to figure out what's my load current on this feeder. Okay. Now, you have to go to your planning department and they're going to tell you, whoa, this is the loading of my feeder. There was some type of MVA level load. So once you get that from your planning department, you can figure out your load current. So high load, it's just like any other three-phase current calculations. Just burn this in your brain. MVA of the load, remember, it's three-phase power, which anytime they give you power is going to be three-phase. Divide by square root of 3 times your kV line to line. Okay. And so most people end up forgetting square root of 3, and so the numbers are all jacked up. So just anytime you do low current, just remember MVA divided by root 3 times kV. Okay. The other place we're going to see this is typically is in transformers. This is transformer protection. Now you see there's two relays. This is going to be your low voltage protection. And then this one right here will be your high voltage transformer protection. Okay, so we typically, if we can, we put a relay on the high side and we put it on the low side. And then you have these two boxes. These are two circuit breakers. So this is a circuit breaker, our high voltage circuit breaker, and our low voltage circuit breaker. Okay. So how do we figure out the low current there? So there's actually two of them. Okay, depending on your high side or low side. So your I for your transformer, so sorry, I load. I load is going to be, again, the MVA to transformer. So the transformer MVA three-phase. Okay, because the MVA to transformer is how much current, is how much power could push through without hurting itself. Divided by square root of 3 times kV, line to line. Now there's one big thing you gotta realize is this kV right here is going to change. You have to say, do I want my low voltage side or my high voltage side? Okay. So if I'm asking, well, what's my low voltage current? Well, you're going to put your low voltage in this equation. If I want to put my high side current, you're going to put your high voltage into this equation. Okay. Because remember, it's a transformer, it has turns ratio, right? It's going to change the current. Most likely the high voltage current is going to be lower. The low voltage current is going to be much bigger. Okay. And, don't swap, whichever one, let's say we calculate low voltage current. That's going to be the current to use for the low voltage over current relay. Okay. High voltage current is going to be used for the high voltage over current relay on the high side. Okay. So that's kind of the main formula we use, right? So that's to find your full load amps. So you could do your 150% full load amps. The other thing we said is you got to look at your minimum pickup. You need to be 50% of your minimum, you look at your minimum fault current. You need to be 50% of your minimum fault current. So the next big thing is, well, how do I find the minimum fault current? That's very, very important as well. There's two ways to do this. If your system is small enough, you can hand calculate it and use symmetrical components, which we learned before. right? So for example, you have a single line to ground fault. Single line to ground faults are typically the minimum fault of your system because they only involve one phase. A three-phase fault will most likely be much higher because you're using all three phases, faulting them, and there's going to be more power because there's so much power per phase. So single line to ground, typically the smallest. Now, to make it even more minimum level is we can add fault resistance. Okay. So you know that ZF we ignored before? This ZF is what we'll add in, and we could put this somewhere between 20 to 40 ohms. Okay. And the idea is this fault resistance should mimic a tree branch or some type of like debris that landed on the wire and it's not giving us a solid path to ground. Okay, because the tree limb does have impedance. And the more impedance you put in the circuit, the lower the fault current is going to be. So again, minimal fault current is we got to think about what point do we have the highest impedance during the fault, and that's our minimum fault level. Okay. Again, it's impossible to go out there and look at the impedance of a tree branch when it drops, right? You don't have time to go out there and do it. So as an industry, we typically say somewhere between add 20 to 40 ohms of fault resistance to your circuit. That's going to be your minimum level. Okay. Method 2, when your system is more complex, where you can't just do hand calculations, you have to use some type of short circuit software, right? There's lots of different ones, and each one, once you learn one, the other ones are all roughly similar, but there's no question to ask. You're going to have to learn new software. Okay. If you're going to be a protection engineer, you're going to learn one of these systems. At Sac State, we have ETAP, which is a company that has short circuit modeling in it. And we're going to try to teach you ETAP in this course during the lab section. Okay. There's other companies that use it, like Aspen is another one, Easy Power, and so on and so on. Okay. But yes, it's pretty much learning a new software and how that operates, Welcome to power engineering, where you use software for everything. Okay. So with that being said, typically we like to do our little breaks. So let's go ahead and take our 20-minute break. Here's an example problem for you to do during that 20-minute break, and we'll come back and check your answer. So just give you a rough idea, low overcurrent protection example. So here's your feeder, right? Your load is 8 MVA. You're on a 7.62 kV bus. You're running 100% capacity. So you're using all 8 MVA of that power. Your CTR is 800 to 5 for this relay. So calculate the load current. So let's figure I load right here. Then let's look at our pickup settings, which is 150% of full load current or full load amps. And then C is, well, let's check. We have a minimum fault current. Is our minimum fault current, our minimum fault current is 2400 amps. We looked at through software. Does this still trip the circuit breaker? So let's check to make sure the relay will still operate in that minimum fault current level. Okay, so kind of do some analysis to see if 2400 amps hits that pickup settings, and if it's the pickup setting or higher, then you trip the circuit breaker. Okay, so everybody, let's go ahead and work in this, and we'll come back in 20 minutes and check your answers. We'll see you then. All right, welcome back. Let's go ahead and check our overcurrent protection example that we're working on through the break. So if you recall, we had a load at 8 MVA and 7.62 kV bus running 100% capacity. So first off, we can figure our load current. Load current is always three-phase MVA. Divide by √3 times kV line to line. So 8 divided by √3 times 7.62 is 606.1 amps. So that is our load current going through the feeder. Next, we're going to calculate the pickup setting to equal 150% of the full load current. So here we need to go into secondary current. So if you remember, you take your load current divided by your CT ratio. We have 800 to 5 CT, which is a 160 CTR. So you do 606 divided by 160. So our secondary current flowing into the relay when the circuit is fully loaded is about 3.79 amps. So remember, we need a pretty good margin of error. So we put 150% of that as a pickup. So 150% of 3.979 is 5.67. We typically would try to round to 1 decimal point off. So I would say 5.7 is fine. If you have mechanical relays, they're probably in whole number, so you're going to have to round this up to 6 most likely. Okay, so now we have our setting of 5.7. So we got to ask ourselves, if we see our minimum fault, is it going to trip the circuit breaker? Well, if our minimum fault current is 2400 amps, does it trip it? Well, the easiest thing to do is look at this, look at how much current is flowing into the relay itself. Our fault current is 2400 divided by CTR. So during a minimum fault, we're going to have 15 amps flowing into the relay. Is this 15 amps greater than a pickup value? Yes, by a pretty large margin, right? Let's say we rounded up to 6, 15 to 6, that's over 200%. So yes, we will trip. And this is a correctly sized, this is a correctly designed overcurrent relay, okay, with the almost perfect, in my opinion, pretty perfect tap setting, okay. So that's how you do tap settings, or sorry, pickup settings for all the relays you're going to encounter, whatever the low current is. Just base it off of that. Do a quick check with a minimum fault current to make sure you will still trip. Okay, so now I want to talk about time delays. So if you notice, we always talk about 50 and 51. 51 has a time delay involved. And so we ask ourselves, why do we build in some type of time delay? Okay. So recall that these relays, a 51 relay is a time over current relay. There is a time built-in time delay. And the question will be like, well, if there's a time delay, why do we want a time delay to begin with? Don't we want to trip as fast as physically possible? I'm like, yes, we do want to trip as fast as possible, but we still need to coordinate with other relays. Remember, we have primary and backup protection. If we're going to serve as a backup protection, we need to have a small mounted time delay to let the primary protection operate first. So we do put in time delays to help coordinate with other relays. All right. And I'm going to type in primary versus, that's a Y, backup protection. Okay. Okay, so if we want to act as fast as physically possible in a worst case scenario, so meaning this is the hardest hitting fault in the system, it's the most dangerous one, we would exclusively use a 50 instantaneous, so people just put inst dot overcurrent relay. Okay. This has no intentional time delay. It will trip as fast as physically possible. No delay. Okay. Now, what about everything else besides the worst case? This is where that combo relay we're talking about, that 50-51 combination will come in. Okay. We can use the 51 relay, the 51 element to coordinate with other relays for we call mid-range faults. So mid-range faults are basically your minimum fault currents and somewhere in the middle, right? So these type of faults it's not going to instantly blow up the system, but if you leave it on for like half a second or 1 second, you will actually do damage, okay? So this gives us the opportunity to coordinate between different relays. If we go to the maximum range, we need to make sure we use a 50 relay, because for, oops, let me write that a little better. The most dangerous situations, most dangerous situations. Okay. And again, this is our max range or max faults. Okay. So the absolute maximum three-phase voltage fault, 30,000 amps, 20,000 amps. We need to make sure that instantaneous relay will pick that up. Okay. So that's where we're going to use both of them in tandem. And when you go out there and program these relays, you're going to be programming both a 50 and a 51 element. Okay. So now we're going to use both of them together. Let's ask ourselves, kind of like have a quote cheat sheet, how are we going to do the settings? So remember, just a recall, check to make sure the pickup is 150% of full load amps. That's a first design step. Number two, check to make sure a minimum fault will trip the relay. Okay. And you could, again, use software simulation. A good rule of thumb we could say is about 200% full load amps is your minimum fault. So let's check at 200% full load amps. The relay should start operating. Okay. Now, that's for the 51 element. Within the relay, you're going to have a second 50 pickup you're going to have to program. This one, again, worst case scenario, we're looking at about 1000% full load amps as the settings. No time delay. Okay. So what this means is if we get to 10 times the load current, that's really bad. There should be a trip, an instant trip. Because 10 times your full load amp is you're going to seriously do damage, right? This is most likely in the 10,000 amp range-ish, or at least like 8,000 amps. And that needs to get off the system as fast as physically possible. Okay, so let's go ahead and show you a little more holistic picture of how to and where to design our overcurrent settings. So here's a very typical single transformer substation. So you have your high voltage side right here from the transmission side. You got your low voltage side. You got your main transformer right here. And then you got your feeder 1 and feeder 2 going to your residential area. So let's go ahead and do settings for all these relays. So let's do the first one is this one on the left side. So left loads pickup. Well, we got to ask ourselves, what is my load current? Okay, so here we have left load, we have 1000 amps at a CTR of 1205. So our 50 element will be, or 51 pickup will be 150% full load amps. So you can tell full load amps by your load current divided by your CTR. Okay, now I already gave you the low current, so this is 1.5 times 1000, and 1205 is 240. Okay, so we go ahead and number crunch that. I got my pickup of 6.25 amps. Okay, so that is my 51 element. And let's go ahead and do our 50 element. So again, this is the same one. This is 1000% against the same full load amps, which is I load over CTR. Okay, go ahead and 10 times 1000 over 240. You guys can see the math going. This is about 41.7 amps. Okay, and so this is for our 50 element. Okay, so 50 relay and then our 51 relay. Okay. Now you can see right here, I have a 50/51 because I typically package one relay, but over here I just want to make sure 6.25 is a 51 element pickup, 41.7 is a 50 pickup for the 41.7 is a pickup for the 50 element. Okay, so that's a left-hand load. We got to pretty much do this a few more times. So let's go ahead and do it on the right side. So the right-hand load is a little bit higher, so it's 1400 amps. So again, we're going to do this relay right here. So same process all over again, probably go a little bit faster. So here, 51 pickup, again, 150% full load amps. This is 1.5 times, in our case, 1400 amps over our CTR. Now this is 500 to 5, so this is going to be a 300. Okay. And then this number is going to be 7 amps. Okay. Again, this is for the 51 element. Okay. And let's go ahead and do the 50 pickup. Again, that's 1000% of full load amps. So this is 10 times 1400, which is a low current, divided by CTR 300. And this is going to be 46.7 amps. And that is our pickup for the 50 element. All right, and lastly, let's do the low voltage side of the transformer. So this is going to be this one right here. And here's a low voltage transformer right there. Notice that the CTRs are different for each one because we had to remember we had to size CTR. CT is based on the loading factor. So 51 element right here, standard 150%. So let's go 150%. Full load amps. In this case, is 1.5 times 2400 divided by, so 300 to 5 is a 600 to 1 CT. And this is 6 amps. So 51 element. And then don't forget our 50 pickup again is 1000% times a full load amps. Again, 10 times 240 or 2400 over 600. This is 40 amps. Okay. And that's our 50 element for the low voltage side. So you can see we just go one by one and do the same calculation process. Now, one thing that's good to note is look at these numbers. For the transformer, we have almost double the current of the other ones, yet our pickup are 6 and 40 compared to 7 and 46 compared to 6.25 and 41. So you can see even though the current is drastically different, your pickups are actually not that far off. And that's because it's a CT ratio. You see the CT ratio kind of takes your low current and normalizes it to a standardized 5 amp current that the relay sees. So no matter how big or small our low current is, if we choose a correct CT, the tap settings or the pickup settings on the relays aren't going to be too off. Again, 6 and 40, 7 and 46, 6.25 and 41, they're all roughly the same. And that's good because now we could buy the same relay for all 3 of these points, right? We don't have to buy a relay that's for like 1 and 2 amps, another one for 6 and 7, another one's for 30 and 40. We buy the same relay for all instances of our overcurrent protection, and we'll let the CT do the normalization from various low currents all the way to the standard 5 amp secondary. Okay, so in this particular case, if you were working here, you'd probably go to SCL and buy 751, SCL 751 relay 3 times and put it for all 3 of these on points. Okay. Oh, we got one more. Sorry. Right. So another question would be, actually, no, sorry. I think we'll go ahead and call it there, and we're going to come back next time and start talking about the inverse time over current relay concept. Okay, mainly today, I want to make sure we hit that tap settings and we see how to calculate 51 pickups and 50 pickups. Okay, so let's call it a day here. Thank you for coming. We'll come back next period and we'll keep on going with the time over current relays and finish it up. Okay, so I hope everybody has a good day and catch you later.